Welcome to Spring LIB.
So once again, we're coming into a new problem, and we still have to deal with wavelengths, but this time we do have two yellow flowers. So we have flowers, we have a flower right here, and then we have another one right here. So those are two flowers, and it so happens that the gap between these two flowers is equivalent to 60 centimeters. So that's in centimeters. Obviously, at some point, we can always transform that to meters for purposes of problem solving. But for now, we'll stick to the raw data. So in this case, we're given 60 centimeters. And then there's a line of sight. There's a line of sight that runs, I would say, well, I was going to say parallel, but it's perpendicular. So there's a line, not sign, but line of sight that runs perpendicular in between. It goes all the way up until the eye. So this point right here, this is the eye, and we can maybe expand it a little bit to exaggerate the eye itself. And so the line of sight for the eye is the line of sight happens to be perpendicular. So this is a line of sight, and it so happens that the wavelength. So if this is the line of sight, so the wavelength, this one goes that way, and this one goes that way through the flowers. So this wavelength lambda is given us 550 nanometers. This is the information that's given in the problem, and the actual diameter of the eye, we've exaggerated the eye obviously for purposes of problem solving, but it's just a teeny tiny 5.5 millimeters, and that's expected. Our ultimate goal in this problem is to determine the distance between the flowers and the ID. That's obviously our goal. In this problem, we already see that we do have light going from the flowers, the actual flowers, up until the eye, and there's certain assumptions being made in this particular problem. The assumption is that we happen to be at the limit of resolution. So the flowers are at the limit of resolution. So now we're set up. We have details about the problem, and we're supposed to solve for D. That's our goal, capital D. And so we're going to go ahead and say we have to backtrack a little bit. We have to make a different assumption. Instead of calling this one D, we're actually going to call it L. So that's the distance we're looking for, assuming limits of resolution. So this is L. And then the 60, that's what we're going to call our D. That's giving us D. Our lambda is 550 nanometers. And then the diameter, the small d, this is a small d, is 5.5 millimeters. That's the information that's given. Obviously, our angular separation, and that's based on the resolution. This one right here, theta r, is given us theta r equals to 1.22 lambda over small d. That's our theta r. And then we're going to go ahead and use algebra. So theta r is also equivalent to d over L. So these two are the same, and we can make them equal. So d obviously is going to be theta r times L. That's the way we're seeing it. D is theta r times L, but since theta r is 1.22 lambda over d, we could do that replacement. So 1.22 lambda all over small d. That's our theta r times L. And algebraic manipulation going on right here. Since we have d, we want to solve for L. So we'll divide both sides by 1.22 lambda over d. On both sides, 1.22 lambda over d. So then L simply becomes capital D small d all over 1.22 lambda. And now we're at a point where we can plug in the specific values we're given. Remember, we have to change meters into centimeters into meters. 1 meter is 100 centimeter. That's the value of d. And then on the smaller side, we have to do the same thing. So we do have 5.5 times 1 meter over 1,000 millimeters. This is also in millimeters. So we're simplifying this problem. Remember, you can see on the side that 1 centimeter is 10 millimeters. And 1 meter is 100 centimeter. So 1 meter has to be 1,000 millimeters. That's the way you're seeing it. Because 1 meter is 100 centimeters, you multiply that by 100. That's our numerator. And then 1.22 times lambda. Lambda is 550. Change that to meters. So times 1 meter of 10 to the 9 nanometers. I'm going to go ahead and simplify that problem, and we end up having L being equivalent to 4.918 times 10 to the 3 meters. 4.918 times 10 to the 3 meters. So once again, just a quick recap. We did have a problem where we were given the lambda. That's the wavelength of light. Our eye is right here, which is this line of sight is perpendicular to these two flowers, and we're supposed to find the gap between our eye and the flowers. The gap between the two flowers is 60, and the diameter of our eye is 5.5 millimeters. We do have to change those units into meters, but before that we compare the values, the formulas for theta r, which is the angle of resolution, and then we plug in the numbers and we end up having 4.918 times 10 to the 3. So hope you enjoyed the problem. Feel free to send any questions or comments, and have a wonderful day.